All right, so this is Physics 1B for September 21st. Today we're going to continue to talk about heat transfer processes. Last time we discussed specific heat, which is the rate at which a material heats up based on how much heat that you put into it. We're going to use that to solve a type of problems that's often called calorimetry. And then we're going to talk about latent heat, which refers to phase change. The heat involved in a phase change, like going from a solid to a liquid, like when ice melts. And then at the end, we'll talk about different mechanisms of heat transfer, which was like, you probably heard of these before. It's some course you've taken before, or just the words you probably know. Conduction, convection, and radiation. And we'll do mathematical problems for this one and this one. We'll just talk about convection in general, as we don't have a good model of it for this class. Yeah, I wanted to get started, though, with a little bit of a kind of, I guess you'd call this a demo, of how specific heat works. So specific heat is the idea that if I have two different objects, like iron and brick, or iron and water, for example, that those objects will heat up at different rates. Okay, so if I take the iron and the water and I put this on here, and I give both of them a thermometer, and then what we'll do is we'll link these two heaters so that I can cool them off at the same time. So we're going to cool these down to as low as they will go. You might have noticed the water took a little longer to get there. They were all initially at the same temperature. So now you guys can tell me, if I apply heat to these two objects, which one is going to get hotter faster? Which one is going to really reach a higher temperature faster? Is it going to be the water, or is it going to be the iron? The iron. And how do you know? How do you know it's going to be the iron? What's up? More conductive? It's not really the reason. It's because it has a lower specific heat. And the reason it has lower specific heat, maybe that's because it's more conductive, but fundamentally it's because it has water has a much higher specific heat. It takes more energy to heat the water than it does to heat the iron, right? And maybe that's related to conductivity, I don't know. But if I put on here a piece of iron and a piece of copper, which we don't have, but we could talk about what happened there too. Okay, so we heat these up, and you see the iron is raising in temperature very quickly, much more quickly than the water. So you guys are right, it's the iron that heats up faster. So here, let's cool these back down. So let's test what you guys said with the brick. Now, I don't know anything about the specific heat of bricks. Do you guys? Do you know which has a larger specific heat between brick and iron? Anyone know? You can look it up if you want to. You think the specific heat of brick is higher than iron? So you believe that when I heat these up, just like what happened with the water, that the brick is not going to get as hot. Is that the idea? So who thinks the iron is going to heat up faster? And who thinks the brick is going to heat up faster? Anyone think the iron will heat up faster than the brick? You guys think the iron will? Does anyone think the brick will heat up faster than the iron? Tyros has brick ovens. Brick will take longer to cool down. All right, so let's cool these things real quick, and let's heat them up. Now they look close, but which one is winning? I think it's the brick that's winning, right? It appears that the brick is able to, it appears that it takes less heat to heat the brick up. That's opposite to what you thought, right? I just want to be clear. It is opposite to what you guys thought, right? I don't think anybody said that they thought the brick would heat up faster, right? Just acknowledging it. Okay. It's opposite of what I thought, too. Because I was thinking, specific heat is related to conductivity. And maybe it isn't. But we can, investigate that idea, because I have this list from before of different specific heats. And we could look at two things on here. Now, brick is not on this list. And you guys could go look up the specific heat of brick if you want to. There's iron right there, right? 470. It looks like iron and copper have pretty similar specific heats. Copper, I know for a fact, is a really good conductor, but aluminum is also a really good conductor. Okay, and we can investigate this later because we're going to talk about conductivity, and I've got another chart, so we can maybe put these side by side later. But I'm not sure that conductivity and specific heat are necessarily connected. You know what I mean? Because look at marble. Marble has almost the same specific heat as aluminum. I mean, it's basically the same number. They're both about 900, right? To one significant figure. And marble it's not a good conductor of electricity, but maybe it's a good conductor of heat? I don't know. Anyway, so specific heat, not the same thing as conductivity. That's kind of the whole point of what I wanted to say with this, is just they're not synonymous with each other, right? What about the olive oil? How's the olive oil going to compare to like the water, for example? Any idea with that? Water has one of the highest specific heats of anything, right? So one would assume probably the olive oil is going to heat up faster? I don't know. Let's see. Yeah, it does. You can test it in the kitchen. Olive oil will very, very quickly start to smoke when you heat it in the kitchen, right? If you take a thin amount of olive oil and you put it in a pan, you start to heat it up. If you don't like put something in there quickly, like some meat or some vegetables or something then the olive oil will really quickly smoke. Whereas water takes a long time to vaporize, right? Okay. What else can we do with this? There's not much else you can do with this, I don't think. I could probably do something like this to show you these little energy symbols, but the other piece of this is really related to just energy itself. This would be something that I might show in like a 1A class, where you can get the idea that you can heat up water through motion. Anyway, so that's something for like a 1A course when you're discussing energy transfers. All right, so let's do some problems with specific heat, and let me kind of just remind you guys really quickly how we do these things. So we discussed last time this idea of what's called specific heat. We use the symbol C to represent specific heat of a material. It is related to how much energy you need to put into the object per unit mass in order to raise the temperature by 1 degree. And our relationship is that the amount of heat that you need, Q, so Q is heat, is equal to the mass of the substance multiplied by the specific heat, and then multiplied by the temperature change. And this temperature change can be written in Celsius or Kelvin. It doesn't really matter because it's a difference. Okay. When you see just one T in an equation, like without the delta, it's probably going to be Kelvin, as we'll see in some equations later on. But if there's a delta in the equation, then it doesn't matter because the temperature difference in Celsius and Kelvin is exactly the same. 1 degree Kelvin increase is the same as 1 degree Celsius increase, but 1 degree Kelvin is not the same thing as 1 degree Celsius, because 1 degree Celsius is just a little bit above the freezing point of water, whereas 1 degree Kelvin is 1 degree above absolute zero. So here's a problem that we can do with this, and these kind of problems are called calorimetry problems. I don't know what you guys study in chemistry. I just remember when I took chemistry in high school that we did problems like this. I'm going to assume you probably did problems like this, but I don't know. Maybe some of you haven't taken chemistry. It's probably pretty common that you don't necessarily have to take chemistry to get this far along in physics. But if you have, this will probably be a little bit of a repetition from that, but that's not necessarily a bad thing. So, all right, let's read the problem. It says, a camper pours 0.3 kilograms of coffee, initially in a pot at 70 degrees Celsius, into a 0.12 kilogram aluminum cup that's initially at 20 degrees Celsius. What is the equilibrium temperature? And we're going to assume the coffee has the same specific heat of water and that no heat is exchanged with the surroundings. Okay. That part is probably a ridiculous assumption, but this is a physics problem, and we often make ridiculous assumptions in order to, prevent it from being too complicated. I left off one other thing here, which is basically that in order to solve these calorimetry problems, the kind of general thing you need to do is assume that the sum of all heat transfers is 0. So basically, we're just going to say summing up all of the possible heat transfers for each of the individual elements, Q1 plus Q2 plus Q3, etc., should be equal to 0. That's going to be basically the way that we do it. We use these two equations. And then when we learn about latent heat, we'll also use one more piece that tells us how much heat you need to actually change phases. Okay? So let's write down all the information that we have right here. So there are, how many different substances are there here that are going to show up in this equation here? We've got coffee, right? For which we know what the mass is. It's 0.3, so let's write that down. It's coffee and aluminum, so we'll use M sub C for coffee. We also know its initial temperature, so I'm going to say the initial temperature. Where to put the C now? I kind of want to put the C up here, so it's not, but I'll put it down here. The initial temperature of the coffee is 70 degrees Celsius. We're also going to need to know what the specific heat of our coffee is. In this case, we're going to use the specific heat of water, which I think is like 4190. The unit for this is joules per kg degrees Celsius. Let's just make sure. And we're going to need aluminum too, so we'll look at this diagram. So water is 4190 and aluminum is 910. So let's write that one down too. So then we've got our aluminum. The aluminum has a, that's the cup, right? So we're basically, I should have drawn a picture for this, right? So basically we've got a cup and we're pouring coffee into it, right? And when we pour the coffee in, so here's our coffee inside of here. We know the coffee starts off at 70 degrees Celsius. The cup starts off at what? 20 degrees Celsius. And we want to figure out what is the final state temperature of the system. What's the common temperature T? That's our goal. Obviously, they're going to come to some equilibrium. What is the number? Is it halfway in between? Yeah, that's what we're looking to do. Okay, so the aluminum has a mass of 0.12. And a temperature. So initial temperature is 20 degrees Celsius. For the sake of keeping things simple, let's only put subscripts on the coffee. Okay. So this would be, let's get back over here. Specific heat of coffee, and this will be a specific heat of aluminum, which we'll just call C. And we said, what was it? I forgot already. Was it 910? Let's see. Oh, and just saying yes, so we'll go with that. All right, so we just really have two equations here. We've got this one, and we've got this one. And the sum of all heat transfers should be equal to 0. How can it add to 0? Well, for one of these objects, the aluminum, the temperature is going to go up. For the other object, the temperature is going to go down. So one of them is going to have, I think this one, positive Q, and this one will have a negative Q, because it's losing temperature. All right, so let's work this out. So if we say from this equation here, we can write that if I take the energy transfer for the coffee, and I add to that the energy transfer for the aluminum, they should add to 0. For the coffee, we're going to write this, I always call this the MCAT equation because it looks like MCAT, kind of. So you have mass of coffee times specific heat of coffee times delta T for the coffee. And what is delta T? We can write that in a slightly different way. We can just write it as whatever the final temperature of our system is, which I'm just going to call T, minus the initial temperature of the coffee. Okay, that is the whole equation for the coffee. And then we add for the aluminum. So we're just going to call that just MC, and then initial temperature subtracted away from whatever our final temperature is. And within this equation, there's really only one unknown. This is our unknown right here. The t's are what we're solving for. So all we need to do is just isolate the t. So let's put all the numbers in at the end. and do that. So what do we want to do? I guess we want to add, really want to multiply through these equations, right? So we're going to have, this is going to be kind of a long equation. Oops. Let's keep it with black. Okay, first term, we just expand that out. We've got MC CC times T minus. And then we just rearrange, moving all the negative signs to the right-hand side of the equation. I'm going to scroll down just a little bit here. So this becomes MC CC plus MC times T. I'm just factoring out from that term and that term, the T, and then I'm adding everything else to the right-hand side. And then we can solve for the final temperature. If you guys have any questions at all, please feel free to ask. So our final temperature is going to be this whole thing divided by that coefficient. And you can tell from the units here that we've got mass times specific heat in the numerator and the denominator. So you're going to get the right units no matter what. And now it's just a matter of plugging all these numbers in. Mass of the C is the coffee, right? M coffee is 0.3. Specific heat of the coffee, we're using water. Initial temperature of the coffee was 70. Okay, plus mass of the aluminum was 0.12. Probably gonna run out of room here. We can just zoom out though. Specific heat of aluminum was 910. Actually, we'll just scooch over to the right a little bit. That'll give us some room. I can still see all these numbers. Yeah, so 910 joules per kilogram degree Celsius. And then that's multiplied by Ti, which is 20. Okay, and then we divide all that stuff by this coefficient. Plus this one. That's a lot of numbers. A lot of numbers in this equation. Can y'all calculate that for me, please? Tell me what you get. I'll do the same if I can find my phone. I think it's in the other room. BRB. Anyone get an answer? Oh, look, you guys have 66 degrees Celsius. Cool. All right, you guys all got the same answer, so I'm gonna kind of assume it's right. We could also try to figure out if that's a reasonable number, so let's do that too. So our final answer you're saying is 66 degrees Celsius. Now, is that reasonable? Let's think about this. Here, let's go back to here. Zoom out just a little bit so we can see everything. So it appears as though our final answer is closer to the temperature of which substance initially? Which one was 70 degrees? It was the coffee, right? Is it reasonable to think that the final temperature we would get would be closer to the coffee's initial temperature? And why would that be the case? Has a higher specific heat, yep. there was also more of it too, right? The mass matters as well. The mass matters as well. Because mass and specific heat show up both in the same equation. You know, they both have the same weight in the equation. Specific heat, however, usually is a pretty big number. So you'd have to have a very large mass, like let's say 1,000 kilograms, in order for the mass to be affected, you know. And then as Ruja says, it takes longer to lose heat, the water, and the aluminum heats up faster. That's right. Okay, so hopefully that's pretty straightforward for y'all. I know these problems, they can get really tricky when there's a lot of different substances, but I'm just curious. Have you guys seen these before? Like, have you seen these? Okay, and do you do very much of it in chemistry, or is it like an afterthought, not something you really you do? Okay. Well, hopefully this homework will be pretty easy for y'all then, because it's mostly just a lot of specific heat problems. All right. So the next thing to talk about then is to talk about what happens when we introduce phase change into this process, right? So let's talk about phase changes. This is where these can get a little bit tricky. So we'll do a little intro here, and then I'll show you these equations. Okay, so when an object goes and changes its phase, and what do we mean by phase? We mean there are these states that objects, matter, can exist in, and the most common ones that we know about are solid, liquid, and gas, right? Water in its solid form is ice, in its liquid form it's water, and in its vapor form, or in its gaseous form, it's called water vapor, or steam, commonly just called steam, right? Now, if I want to know how much energy I need to actually melt an ice cube, then I need to know something about the property of the material of ice. And not all substances are the same. Each substance is going to have a different amount of heat necessary to actually force it to change its phase. And for an object to go from a solid to a liquid, then we define something, that process is called melting. Then we need to know something about the material. And the thing that we need to know is what's called latent heat. For this case, we need something that's called the latent heat of, now the name escapes me. It's the latent heat of, can you guys help me? You probably know. You've done this before, right? I know what the other one is. If you go from liquid to gas, this is called the latent heat of vaporization. Latent heat of fusion. Thank you, that's right. Latent heat of fusion. Fusion is kind of like the opposite of melting, because it turns out that the latent heat to go from liquid to solid is the same as the latent heat to go from solid to liquid, and the same thing to go from gas to liquid. It's a two-way process. So these are quantities that you're going to have to look up in a table, but we can describe the heat transfer Q, just like with our previous equation with specific heat, by just taking the mass of the material and multiplying by the latent heat for that particular phase change. This is our definition of how this is done. So latent heat is effectively the amount of energy that you need to put into the object in order to cause it to change its phase. Okay, and then I believe over here I probably have, here it is. Not specific heat. There's latent heat. It's called latent heat. What does that mean? What does the phrase latent heat mean? Does anyone know? Let's scoot this down just a little bit. Anyone know why it's called latent heat? Where that comes from? I guess we could ask what the word latent means. Does anyone know what the word latent means? You can go look it up on the internet if you want to. Latency means like lag. Huh. Does it? I mean, we certainly use... That phrase is definitely used in like gaming for sure. Latency? Is that what they call that? Yeah. I thought the word latent meant hidden. But maybe it does mean lag. If it means lag, that makes a lot of sense. Because it's essentially like a lag in a temperature change because the object has to change phases, right? I'll give you an example of how this works. So if you have, let's say you have a cup, okay? And you just fill that cup with ice cubes, okay? So you just put a bunch of ice cubes into your cup. So you've got a bunch of ice cubes. No ice, no water, just ice cubes, right? You just fill it up with ice cubes. And I check the temperature of this. This is just ice, right? I check the temperature of this. And you guys tell me, what's the temperature of the ice going to be? I put a thermometer in here. What's it going to read? So I stick a thermometer in here. What's the thermometer read? It's going to read 0 degrees Celsius. Right? So Delvino says latent talents. That's like hidden talents, right? Like talents that are like you have within you, but that you haven't been exposed to yet, or something like this. Like, you're not going to know how good you are at riding a bike until you're actually able to ride the bike. I don't know. All right. So let's say given some time, so let some time pass, like, but not a long amount of time, just enough time that what we're left with in here is ice plus water. Okay, so now we've got a little bit of liquid water, and now we've still got ice cubes, but those ice cubes are now kind of just, they're floating in the water, right? So we've got our ice in here, and a lot of the ice is melted. Okay, so you've got much smaller pieces of ice maybe, or something like this. So now what we have is ice plus water, or ice water. And I ask again, what's the temperature of this going to be? It's also 0 degrees Celsius. Well, given enough time, one would assume that the ice is exposed to its environment, so it's certainly taking on heat. But for whatever reason, even when it melts, the water doesn't heat up. The ice is still 0 degrees Celsius, and the water is still 0 degrees Celsius to a certain extent. If it's a really tall glass, the water at the very bottom of the glass may actually be a little bit warmer than the water at the top that's more directly in contact with the ice. But that's a different story. As long as the cup is small enough, this is effectively going to be true. All right? This is effectively going to be true. That even though there's ice plus water, the temperature is still going to be 0 degrees Celsius. And at least with the theory that we're going to describe today, which is only approximately true, but it's still kind of true, as long as there is at least some ice in the water, the temperature will still be 0 degrees Celsius. The temperature will still be 0 degrees Celsius. So that makes ice really good at cooling down our drinks because it keeps the drink cold as long as you still have ice in it, right? And you can cool it back down just by adding more ice to it. This is basically what latent heat is. The fact that you get, flowing into the substance is heat, right? You've got heat coming in, but there's no temperature change. So latent heat refers to a heat transfer in which the temperature does not change. Specific heat refers to a heat transfer Q where there is a temperature change. So that's, yeah. And down here we've got something you can look up in a table, right? You've got things in this, here you've got like water. You know what the melting point is. Here's the latent heat of fusion, 334 times 10 to the 3, so 334,000. That's how much joules of energy you need to melt 1 kilogram of water. You need 334,000. And that might seem like a really big number, and I guess it is. I mean, when you compare it to other things on this table, it definitely has the highest latent heat of fusion, right? Maybe not for all substances. And then over here, you look at water and you check its boiling point when it goes from water to water vapor. And there, you've got about a factor of 10 higher. About 2.2 million is the latent heat of fusion or vaporization for water. there's two others that show up as well. There's something called a latent heat of combustion for when something is burnt, like when you burn charcoal or when you burn a piece of paper. There's a latent heat of combustion. And there is also a latent heat of sublimation, where an object goes directly from solid to gas, as happens with big mounds of snow on cold days, where the snow literally sublimates directly from solid to gas. And there's other types of situations where an object goes straight from solid to gas. There's a really common one that is sometimes used in demos called dry ice. What is dry ice? Do you guys know what dry ice is? You can go buy it from the store. Like you can go to Vaughn's and you can buy dry ice. What is dry ice? It's CO2. That's right, Tom. It's just frozen carbon dioxide. And carbon dioxide at standard temperature and pressure, so at whatever, 70 degrees Celsius and 1 atmosphere of pressure, it happens to go directly from the solid form of the dry ice to the gaseous form, which is CO2, right? So that's an example of an object that sublimates, and you would have a latent heat of sublimation as well for that one. And that's something, again, you'd have to go look up or be given to you in a problem. All right, so that's latent heat. And this is a common type of picture that is shown in pretty much all textbooks to kind of describe latent heat. And I don't know if it's particularly useful to you guys, but I find it pretty useful. So on the left in this diagram, we've got temperature going from negative 25 degrees Celsius up to 0, which would be the melting point of water, and then up to 100 degrees and a little bit above. And on the right, on the lower axis here, we have time. Why is it time? Let's read what it says. Graph of temperature versus time for a specimen of water initially in the solid phase ice. Heat is added to the specimen at a constant rate. The temperature remains constant during each phase change. Now, this is where, instead of time right here, it seems like it should be heat, but maybe there's a reason for it, right? They are saying the heat is added at a constant rate, which means the time axis is proportional to the heat axis. So, however you want to think about it. Definitely the case that as you go right on this axis, the heat is being added to the system. All right, so you start off with ice from A to B. You've got this little slant right here that represents ice warming, right? And the slope of that slant is related to the specific heat of ice. So let's think about the slope of that slant versus the slope of this slant. Let's talk about that. So going from A to B, the temperature of the ice goes up because heat is being added to it, and it increases its temperature to 0 degrees Celsius. Once the temperature is at 0 degrees Celsius, you have a combination of ice and water. So from B to C, you've got ice and water. At some point, all of the ice is gone, and only then can the temperature actually increase beyond 0. Right? So now the temperature is increasing, and what will we say about the temperature increase? What would we say about like the slope of this line, C to D, versus the slope from A to B? Which one has a steeper slope? Which one has a steeper slope? A to B. Now, why is that the case? Why is this slope steeper than the slope from C to D? Is it just arbitrary? Or did they do a good job in this picture of indicating reality, or is it just another smaller? What has a smaller specific heat? Which one, ice or water? If you don't remember, I'm pretty sure ice has a specific heat of about 2,000, while water has a specific heat of about 4,000, right? And if you look at the way it's plotted, you can kind of see from this picture right here, we're plotting temperature versus well, it says time, but really versus heat, right? And if we rearrange this equation right here, what we would get is something like this. Final temperature minus initial temperature is equal to the heat that's being added times 1 over MC. So if you wanted to think about this as like a, I don't know, just your normal like function, then Q would be like your x-axis. Mass is probably a constant, so we just like put that inside of there. So 1 over c represents your slope, right? So the thing with the smaller slope is going to have, the thing with the smaller specific heat will have a sharper slope, right? Does that make sense? So just the reason is, as Tom said, smaller specific heat. Another way to think about it in a less mathematical way would just be smaller specific heat, therefore it's going to heat up faster, right? It's going to have a faster temperature increase. Does that all make sense? Okay, so going from B to C, temperature stays constant at 0. And then going from C to D, now you've got water. It's being heated from 0 up to 100. Maybe is what would happen if you're like heating water up on a stove. And you've got that gradual increase in temperature. But then once it starts to boil, now you're going to get a combination of liquid water and steam, right? And you can kind of see just graphically that you have to put a lot more energy in the water to make it boil than you do to just, melt it. And that's probably consistent with your experience too. If you put a big pot of water on the stove and you turn on the heat, it takes a long time to boil water, right? Depending on how much water you have. Now what's described here is for all of the water to completely turn into steam, that's point E. And then now what you've got is just the steam being warmed up from there on out. And again, the slope of this line and this line they look like the same slope, don't they? Don't they look like about the same slope here? What do you guys think? Do they look the same? Is that reasonable? What is the specific heat of steam? I don't know if that's in our list here. It's probably not. We got water, liquid, and water ice. But I bet if you look up the specific heat of steam, then we can figure out whether they're lying to us or whether this is an accurate representation. Can someone look that up real quick? What's the specific heat of steam? And while you're doing that, I'll get set up with this next problem. This is the one we want to do, right? Yeah, I think so. You want to look it up yet? I mean, I can always do it myself, but... What's the specific heat of steam? All right, so they're saying it's about the same as ice, basically. Which means, yeah, they're kind of being misleading here. This boiling point here, or from E to F, should probably have about the same slope as A to B. Yeah, whatever. Okay, so let's look at how we would solve a problem with this. We're going to need this table here, but we can just kind of start from here, I think. All right, so this is a problem where we have a change in both temperature and phase. I kind of want to give you guys a shot at solving this by yourselves. The only equations you need are for non-phase change, you've got Q equal to MC delta T. And for a phase change, you've got Q equal to plus or minus, oh God. Q is plus or minus the mass multiplied by the latent heat of fusion. In this problem, you have a glass that contains 0.25 kilograms of omnicolor, which we're going to say is mostly water, initially at a temperature of 25 degrees Celsius. How much ice, initially at negative 20 degrees Celsius, must you add to obtain a final temperature of 0 degrees Celsius with all the ice melted? And we're supposed to ignore the heat capacity of the glass. Although we wouldn't have to if we just knew how much mass there was. So I kind of wish that was not ignored, but for now this is fine. So we're given kind of two substances here. You've got the cola, and then you've got the ice. We know that for the cola we're given the mass. The ice, we don't know what the ice mass is, so the mass of the ice will be an unknown. We know the ice's temperature, at least the initial temperature of the ice, is negative 20. the water starts at 25 degrees Celsius. With a cola. That's all we know, right? And we know in both cases that the final temperature is going to be 0 degrees Celsius. But in addition, all of the ice has to melt. And again, what we're going to be doing for this is the sum of all Q's should be equal to 0. So the ice needs to not only increase its temperature from negative 20 up to 0, but it also needs to melt. The specific heat of ice, I think we saw, was 2190. And the specific heat of water, or the specific heat of the cola in this case, is going to be 4190. This is probably not, it's not 2190, it's 2090, isn't it? $2,100, okay. So our goal here is to figure out how much ice, right? So we want to find what the mass of the ice is. This is our goal right here. Let's just solve for this. Do you guys want to take like 5 to 10 minutes and try that out? See if you can't at least set up the equations and try to solve for what the mass of the ice is in this case. So I'll just check back at like 10:51, and if you need more time at that point, just let me know. But I think you should be able to solve this in about 5 to 6 minutes, or at least set it up. Is that enough time to get an answer? Okay, so Cam has put an equation in there. 0.598 kilograms of ice. You want to get that same answer? Do you guys need more time? Anyone want to respond? Do you need more time? Are you done? Either put an answer or say you need more time. There's two options. You can either okay, so close. So Freeman got something pretty close to their number. I'm just gonna take it since no one's saying anything that must have been enough time. It's let's see what we get if we work this out. So our goal here is to use this equation. So we need to write down every single transfer process that we have. Personally, the way I do this is I kind of write it like this. We're going to have the energy that flows into the cola, right? So this is going to be the energy that's required to take the cola from 25 degrees Celsius down to 0 degrees Celsius. I hate how it does that. It just puts these random little marks. The cola has to go from 25 to 0. We also need the temperature, or the heat transfer for the ice to melt. And we also need the heat transfer necessary for the ice to raise its temperature from, negative 20 up to 0. And really, these occur in order, so in order, I don't know if that's the right way to put it, but it goes like this. So both of the objects have to cool down to 0, and then all the ice has to melt, basically. So those are the three transfer processes that we have to put into here. So for the cola, that's going to be a MC delta T process, because it's a temperature change. So you're going to have the mass of your cola times the specific heat of the cola, which we're using water, but whatever, times delta T, and we know what delta T is here. So, I mean, I think it makes sense to put the numbers in now, just for simplicity, because we have a 0 in here, which makes things kind of nice, actually, because this 0 times this will just be 0. Okay. We also need the ice to go from negative 20 degrees Celsius up to 0 degrees Celsius, so this is going to be its final temperature. So you're going to have the mass of your ice times the specific heat of ice, and then times this temperature change. So 0 is the final temperature now, so it's going to be 0 minus negative 20. And then plus, for the ice, we're going to have the mass of our ice, which is ultimately what we're solving for, multiplied by the latent heat of fusion of ice, which we'll look up in a table. I think that the latent heat of fusion for ice to water is it's like 3. You guys are all saying I did something wrong, and I'll check it in just 1 second. Let me just look this up real quick. Where's ice? Water. Fusion 333 times 10 to the third, so it's 33. All right, you guys are right. We're going from 25 degrees Celsius to 0 degrees Celsius, so I've inverted that. That's exactly right. Thank you guys so much. Appreciate that. All right, so
there's our equation. We're solving for the mass of ice. You wish you could do that on paper. Yeah, it's pretty nice, right? Well, you can, right? I could have just done this. I could have put a negative sign in front of it. That would have done the same thing. But it's nice to be able to do it on the screen. So thanks for noticing that. This is the 0 is the final temperature, and the initial temperature was this. Okay, so we've got some terms here that are just 0, and we're solving for mass ice, right? So let's work it out. So what we have is, now let's see, MC times specific heat of the coffee or cola times negative 25, so we'll just put negative 25 degrees Celsius. This one, MICI times 0 is 0, but then you've got the negative 20, so plus mass of the ice, specific heat of ice, and then times 20. And then, plus this. We'll get all the MI terms to the same side and factor them out. So mass of ice times specific heat of ice times 20 degrees Celsius. That's the first term, plus we need the latent heat of fusion of the ice of water. All that should be equal to this term. If we add it to the right-hand side. This starts to look like the equation that you wrote down there. Yeah, the equation that you wrote down, Cam, looks exactly right. So our mass of ice should be equal to and then we can plug in numbers.
We'll just shift this over to the right so I can actually fit all the numbers on the screen without zooming out. So that's our equation.
Plug in the numbers. Specific heat of the cola was 4190. Wait a minute. Something's wrong here. I left something out. Yeah, that's not right. That's better.
Put some parentheses in the wrong place there. Sorry about that. It's the specific heat of ice times 20 and then plus the latent heat of fusion.
So 20 degrees Celsius times this plus that. These should have the same units. They do.
Okay, so what is that?
What do y'all get if you calculate that?
So something like 70 grams, right? These problems are just a whole bunch of algebra along with an understanding of what these things represent. And you got to think about, like, phase changes as well and what effect that has. Okay, do y'all have any questions? Does this roughly make some kind of sense? So there's levels of difficulty to these problems. The first one we did would be kind of the lowest level of difficulty, where you just have two things and the phase doesn't change. And all you have are these MC delta T equations. Second level of difficulty is by inputting a phase change into the problem, which is what happened here. And then the next level of difficulty will be when you have a phase change and a temperature change after that. And that's what we're going to do next. So this is what we'll do next right here. You're welcome to look at it over the break if you want to and try to solve it for yourself. But we'll take a break until like 11:11. And I'll stop the stream. And if you do have any questions, please feel free to ask. I'll leave the screen here for a second and just see if you guys have any questions.